the tool is seeing how long I've actually had a drink, and you can actually change that interval down. We actually allow you to use multiple AI models. RF-DETR here is our proprietary in-house AI model. I'm going to switch over to that just because the level of accuracy is dramatically higher. You can see that it's tracking in real time from my webcam, this nice iced coffee that I have here from Costco. You see the overlap between kind of my lips and the container says, okay, I think you're taking a drink. And so now it's reset the timer. And if you have the whole thing expire, it's actually going to make a noise to remind you to take a drink.
So today we are going to be talking about, oh, wait, hold on a second. It looks like I need to take a drink of water. Here we go. There's my cup. Good. Okay, we did it. All right, so today we're going to be talking about this application that you see here called Hydrovisor, which, as you saw, can help remind people to drink water based on computer vision. And to help us dive into this, we have the creator of the application, Riaz Virani. Riaz, would you like to introduce yourself to everybody?
Hey everyone, I'm on the enterprise team here at Roboflow. So we build tooling for a lot of large companies for things like defect detection, manufacturing, etc. I've been here for I think about 3 months now, so I'm still relatively new to the team, but it's been a lot of fun so far.
Nice. All right. So I am excited to learn more about Hydrovisor, this app that you built, and validating actions. I think you prepared a demo that's a little bit more in depth than the one that I just did a moment ago. Would you mind kind of taking over, sharing the screen, and letting us see what you've prepared?
Yeah, let's do that. All right. So assume everyone can see the screen, or at least someone can see the screen.
You look good. Look good.
Awesome, awesome, awesome. All right. So in the background, you can see our wonderful New York office. Um, so the idea behind this, and by the way, if you want to, the app is just live on a website that anyone can visit, which is this URL hydrovisor.live. So as we're chatting and going through the presentation, if you want to go test it yourself, you just go to that URL and it kind of works. So the genesis of the idea was, what if you are working really hard and you through the day just like forget um to hydrate yourself, right? You forget to drink water. Wouldn't it be amazing if the camera that's staring at you all day long in your face, which is just a webcam, would remind you that you need to take a quick drink, or whatever. So in this case, uh, the tool is seeing how long I've actually had a drink, and you can actually change that interval down. Um, and we'll talk about this a bit later. We actually allow you to use multiple AI models, including this is one that's trained on some data. It's a more public model, but this is based on our RF-DETR here is our proprietary in-house AI model. I'm going to switch over to that just because the level of accuracy is dramatically higher, and I'm sure we'll get into the details of that. The notion is that it is going to be, as you saw, tracking my face. Just taking a second right now since we're on the Zoom to actually download the weights of the model. One of the things to kind of point out is that this is running entirely in your browser. So the model has been trained, but the weights are coming literally and actually using the GPU on your computer. There's no sort of privacy issue. There's no video going anywhere else. So in this case, you can see that it's tracking uh, in real time from my webcam, this nice iced coffee that I have here from Costco. And you see the overlap between kind of my lips and the container over a certain amount of time, and there's some kind of fancy math in there. It says, okay, I think you're taking a drink. And so now it's reset the timer, and you can change that interval to however long you want. You can choose different models. And if you have the whole thing expire, so if we went down in just a little bit of time, it's actually going to make a noise. And optionally, if you during the initial boot said okay, it might send you a notification. So you might have been on a different tab, different application doing some work, and you'll still hear that noise and it'll remind you to take a drink. Tripped it again. So that's really the user interface and the intention behind the app. And the idea is to make it super simple, something anyone could use. Intentionally throttle the frame rate to make it sort of low intensity on the compute of your computer, um, and prove out that we could build something really useful, really quickly, and really easy to use with computer vision, given RoboFlow's tooling.
I actually I had one kind of question about that before we
Yeah,
keep
yeah,
going.
yeah.
Um, Real quick is you mentioned like being able to build this very quickly. I see we got one reaction already from some people liking this. Um,
I wanted to see the like, hey, the next drink timeline, but I was like, just like literally without thinking, like, oh, I feel thirsty. Let me take a sip. And
you've trained yourself to drink too much. Yeah, you're very hydrated. All right. You know, actually, I did want to pop in there real quick because you mentioned being able to create this really quickly. Maybe after you take a drink, you can answer this question.
yeah, yeah. Maybe before it'll keep bugging us over and over, we'll change the interval here and let it.
Nice. Okay, good work. Okay.
Yeah, right, right on. Okay.
Nice. How long did it take you from kind of like inception to it's live online to make this application?
I think it was about 48 hours from like the idea. So one of the reasons the app was even made in the first place was everyone at RoboFlow when they join the company is required to make a computer vision application because you may have people with different backgrounds, and we call it the visionary project. And you can just go to train a model with some data, but I was like, it's more fun for me if it's sort of like a thing I can use. And it's like one of the insights I recognized from at least the enterprise team was. Um, it's not just the computer vision model. A lot of the challenges are the camera. And I was like, okay, well, from what do I have right now? And what's the cameras that are around us everywhere? And there's two of them. There's always one pointed at your face when you're on a computer, so your webcam. Every laptop or desktop has one. And the second one was, on your phone, right? So it seemed natural to me that the webcam was underutilized. And then to actually do the build, you can actually see here if you're a technical person that there's a link to the source code. All the code around this is public. Um, that you can go and browse it, and it has instructions if you're just curious about how it was done, what it's using to take a look. But fundamentally, it's just a React app. Like it's like the simplest build of a React app, and it uses under the hood uh, Inference.js, which is sort of our open source tooling to be able to run models in the browser. Um, and it uses a model that we trained by reason of being so fast is we were able to grab images from just people in the office, but also thousands and thousands of things that are in RoboFlow Universe, which is our sort of GitHub for imagery that's already available. So that in combination of sort of the ready-made tooling meant, the code here is pretty lightweight, um, to be able to build it out because most of the uh, core things are done for you, and really you need just something like, use drinking detection. Essentially, is just taking those key points and mapping them. I won't go too much into the detail of the code. I'm happy to answer specific questions, but um, the
Yes, well,
yeah,
sorry, on that note, I was gonna
yeah,
say I have a question that I
yes,
prepared ahead of time, which is before we kind of get into the models and things like that,
yeah,
for humans, recognizing a specific action is like very easy, right? Like I see a
yes,
person drink some water, I know that they drank some water. Teaching a computer program to recognize an action can be a little bit tricky sometimes, right? Like I'm thinking about a couple of months ago, we had a guest on that was talking about how to teach robotic arms how to pick up pieces of sheet metal. And again,
yeah,
kind of like simple for a human to like pick up an object, but for a
yeah,
computer program, it's like first, figure out where the sheet metal even is.
yeah,
Second, figure out which piece of sheet metal is on top
yeah,
of the pile. Next, understand the shape so that you can determine where the middle is because the robotic arm needs to know where the middle is. And I was like, I had a brand new appreciation for my ability to pick up things based on that.
yes,
Like, oh man, my brain is doing so many
yeah,
things.
yeah,
Um,
100%.
yeah. So, yeah, can you tell me like how for this task of like drinking,
Yeah.
how do you parse the action? Like how do you deal with that problem?
Uh, I had the same challenge, and it was ultimately when I had the idea, I was like, oh, it's a simple action. Like I'll just grab videos of people drinking, and I'll say, here's drinking, not drinking, right? And you end up finding that that's actually kind of a complex task. So the right answer was, I think, similarly to your experience, we ended up breaking down the task, which is like, um, what are the things that if you looked at something would help you deterministically, like kind of set a rules that let you know? And it's basically if you have a face, so first you got to detect a face. and you have something that looks like a drinking apparatus, a cup or glass, drinking is almost always going to be the case where if there is a sufficient overlap for a consistent amount of time of the things that are the lips and the drinking apparatus. So examples like if I do this, uh, it's not going to think I'm drinking, right? Uh, and if I do this, it's not. That was not by default. That was like finding this problem use case by use case. So let's just go with the first problem, face, right? Okay, so we have to detect the face and we have to detect the lips. Luckily, in this case, there is some really great tooling, and where we're actually combining models with Roboflow trained models and non-Roboflow trained. Google has an open source library to do face detection by default. That's what they use for Google Meet. So we're leveraging that and keeping track of only certain key points. Hey, but then what if there's multiple faces in the image, right? So now actually you have to look at the ones that are most likely the person you're wanting to track, which is you, is probably in the center and is probably the biggest one. So if there's like an audience of faces, okay, so first you got to do that. Great. Now you think you can find the face. Second thing is the drinking apparatus. Okay, but is it like a mug, a cup, whatever? So you need to train a model that just detects this on its own. You could try to train a model that even detects its angle. No, this one doesn't. Because it turns out it's harder to do, and you're like, it doesn't actually add much value. So you do a whole bunch of work, but now you've got two models running independently, and now you track the overlap. You have to track those elements and this element overlaps for a sufficient period of time. Deal with the flickering of maybe what the model sometimes has a false image, and is the object still moving really fast? Uh, because all those indicate sort of all other intents. Um, so it's sort of like you and I might know something pretty intuitively that someone is like walking, but if you actually study like roboticists, and it's like, well, it's actually like this angle when they're doing this versus like standing or walking, like there's a lot of like subtleties. So you just gotta think of each steps of like what would have to be true about this situation to mean that we um so that we almost always certainly know that where someone is drinking. And then you work back from those rules and then just kind of build in each of those individually. The reason you do this is just the reliability, right? Like, um, a good example is you've probably seen sometimes it'll like flicker and it'll think I have, something in my hand because it is kind of hard to know given the background and the type of thing. Like, maybe if I do this, it'll probably think that something in the background is like partially in my hand. And if you actually think about it, like a human just kind of intuits the whole scenario very quickly. For a computer vision model, we say, okay, that's kind of okay because we only really care about like what's the confidence level of this over that. Because you're almost always trying to achieve a specific goal, right? So with most computer vision solutions, like, the reality is the notion that it can just sort of look at like a 5-minute video and tell you everything about it, in real time as it's happening is a worse challenge than most of the time you're like, I care about this thing, right? So tell me what has to be true for that thing to be true. Um, and sometimes it's just like you make the mistake and then you put in like code around that edge case.
I
That was probably the
feel
whole second 24 hours of it was figuring that part out. Yeah. Sorry, I mean, I see.
no, no, no. I was gonna say, I feel like a little earlier, one of our colleagues there walking by in the background actually kind of like helped prove one of those things, kind of unwittingly helped
Yeah.
prove it, where he was near the camera and it didn't register him as like the main person to be detecting on. Um, I want to talk. We actually got two questions so
Yeah.
far. We
Yeah.
could talk
Yeah.
about those a little bit. Um, there's one. Sorry, maybe I'll handle one of these questions a little later because I think we have some stuff prepared for that. But real quick, I saw from Jonathan. He mentioned it seems to be 2D lacking depth info when I fake drink, overlapping bounding boxes. It says drinking. I mean, first of all, this was a really kind of quick, fun project that was made in like 48 hours. So I'm sure there's a lot of
Yeah.
things that are like kind of left on the table in terms of some features that you wanted to build.
Mhm.
I was thinking. Well, we do have like the depth anything v2 block.
Mhm.
There are kind of like some models out there if you did really want to try working with
Mhm.
a depth, like if anybody in the audience is maybe wants to take this and make a v2 of it, fork the project.
Yeah.
Um, did you kind of think about like depth or any kind of like in terms of process parsing the process? Is there like some other things that you had to kind of leave on the table because you only spent 48 hours on this?
Yeah, this is actually a really good question. You know, in this specific case, I think of like whenever there's like computer vision challenges, there's sort of like generally two flows. One, which is like, okay, imagine your use case requires you to collect a bunch of media and then work on it where you can your goal is like the highest level of accuracy, right? And in that case, you can pick approaches that are okay with higher latency, with require more compute power, etc. Um, and you could maybe even correct some of the deficiencies in the sort of inference that occurs at the end. And I think in that case, that would actually make a lot of sense. There's a lot of compromises in this solution, mainly because the idea was, um, well, the delivery mechanism and the deployment mechanism is meant to be a real-time interaction that's running, trying to limit the amount of resources used on your computer with models supported by Inference.js that can run. In fact, even the frame rate that you're seeing here in the UI is highly throttled, like really low, intentionally to try to lower the usage of compute. If you have like use cases that are often like, hey, I need to do this reliably in real time, not to say that you can't necessarily do depth anything in real time, um, but you'll often choose a less sophisticated or
Mm.
actually less advanced computer vision solution, given the constraints of the deployment of the camera to inference and back out, which is often something we do notice in sort of the enterprise world, which is often like people want like high frequency defect detection on like a manufacturing line, and so uh, there's a lot of work where we intentionally choose to bypass certain approaches to say, well, if it has to be this reliable, it can't really fail. If it has to only use this much compute, the device and the camera have to be like literally mounted on the line versus being able to use cloud compute. So that's how I would think about that. Like, I actually don't, I think it would be definitely a worthwhile experiment to see if you could make work. At least my thought around this was sort of like how I wanted to deal with the constraints of like how realistic it could be. And so could you run this for several hours behind the scenes? Additionally, I think the other thing I found was there's a lot of progress in that world, but the depth detection models are still potentially uh, more error prone than this sort of simpler approach that we've taken for this use case. Was kind of my quick experiment with it, but that certainly could be an area of expansion, and I could definitely be potentially incorrect. Although I don't think you could do it with Inference.js, at least the way it's written right now.
Cool, cool. All right. There was one question we had that lines up with something else that I wanted to ask about from Vivek. How many hours of video were required to annotate? So could we talk a little bit about like
Yeah.
the custom models that you made and the process that went into that, the amount of data, stuff like that. You mentioned RF-DETR a little bit.
Yeah.
For people who aren't familiar, RF-DETR again is like a model architecture that Roboflow has helped to develop, and it's kind of available open source, but it's available also in kind of like our platform for training as well. Yeah.
Yeah, absolutely. So, this is where, so there's, so the answer, the direct answer to the question was in terms of the videos that were annotated, it was literally three videos from people that were just in our office. And these are three of our coworkers from the New York office that volunteered to just use the photo booth app on their computer to record that video to give us a realistic sample. But if you actually notice here, there's thousands of images. And so in order to collecting all that, the secret power gear was a product called Roboflow Universe, which is sort of Roboflow's like GitHub for letting people share in an open source way images that are annotated. Because right now, I mean, you would kind of struggle. And so we just went and browsed all of these, or I did at least. And you can just see here, there's just like, hey, let's grab a variety of images of sort of just things that are things you could drink out of to make the tooling see different angles and different kinds of things. And there's even after you get that, you can kind of see there's more realistic images too. But these were not annotated by me, right? So these were things that I was kind of browsing and then grabbing images and taking the annotations that were already there. So that was super helpful from a speed perspective because I could kind of leverage the community. And this is not a thing that people consider sensitive most of the time, or I don't know, that's already a kind of public domain item. And then from there, the way Roboflow works is you have this sort of project, you have sort of your source media, um, And in fact, honestly, this project itself is public. You can actually take the models and the media that I've started with if someone else wants to and expand upon it. And then you can actually go and train models. So this is when you can create in this case a data set version. There's 8 here because we started with one data set and I created one called the updated data set. The 3 models you see in that UI are actually these 3 right here at the top, where we took the same data set and augmented them a little bit, resized them, and Roboflow makes it really easy to kind of train different models from the same one. And so we actually trained YOLO V8, which is sort of a more traditional model. But RF-DETR is actually a recent state-of-the-art computer vision model that's a detection transformer that's actually been public, RF meaning Roboflow, that we've open sourced. The official docs don't even say yet that you can use this in Inference.js, but one of the perks of the job is you can go talk to the engineers that work on this stuff and say, like, would it actually work? And they're like, yeah, we just want to update the docs. And so the model that you're actually seeing is getting a higher level of accuracy, and the one that we're using now that's not finding, magical tricking apparatuses everywhere, is actually this RF-DETR small. That is, running, like I said, the weights are up here and it's downloading and running in the compute on your local computer. Uh, and yeah, like you can download the data set that was related to this, and you can also, right now you could go and put your own images in and or download the weights for this, uh, just like I am yourself.
I had a question about that for, detecting a cup. Um, that's something that I imagine would be in some like kind of like really common off-the-shelf models, like,
Mhm.
like O365, stuff like that, right?
Yeah.
Why did you need to make your own model? Was it for the accuracy or was it for the
Yeah.
performance to be able to run in the browser?
Accuracy. Yeah. Like you can find, there's sort of these things off the shelf that'll like detect a it will say they'll detect a cup. They just aren't as accurate, and they are in isolation, but they will sometimes work. In some ways, you'll actually see even our model when we're using the YOLO V8 variant, which YOLO kind of generally, I think, benchmarks off of like Cocoa. But you'll see even with our all extra training data, like it'll sometimes think my hand or whatever is a cup.
Hmm.
And if you try some of the other stuff that's public, you'll notice that. So this is just like the face mesh tooling was really, really accurate, and I'm sure Google has spent billions optimizing that thing or whatever. Uh, but even for something like this, there's also the notion that we want it to be tolerant of like all sorts of drinking kind of units and expand. So you will often get um this is kind of the truth with all AI. Like it's often easy to do like the 80% solution. It's very hard to do the like last 10 or 20, and every sort of level of element of accuracy gets even harder. And you can get a lot of bang for your buck by taking something off the shelf from a public benchmark and actually even fine tuning it further and making your own model. Which for a large language model is often it's kind of frowned upon, but it's sort of the best way to go if you're doing computer vision and you want something that's really, really accurate.
Nice, cool. Okay, we got a bunch of questions about training models. I want to kind of like later, I want to swing back around to training models. In the meantime, I want to kind of switch a little bit in terms of talking about kind of like expanding this into some other domains and kind of like deploying,
Yeah.
like where could this be deployed? Because I saw a couple questions. One is from Chris, and he said, very interested in how to use Inference.js on a video stream coming from an RPI5 with a USB camera using WebRTC, which seems to provide the lowest latency. And then there's one other question that I saw from Dalton, and he said, do you think it's possible to run this code on an ESP32 microcontroller, perhaps using MicroPython? Um, so let's talk a little bit about deployment. I
Yeah.
see here where we're on the Inference.js page again. There was kind of like those two questions are kind of like very two different roads, but I think we can talk about them a little bit in terms of like where you're deploying here, and then maybe if we wanted to deploy to like some other kinds of platforms, right?
Yeah, 100%. Yeah. So those are good questions. Let's start with I think what was the first one in terms of, if you had a stream coming from WebRTC, how would you interact with Inference.js? If the idea with Inference.js is it's pulling your models and wherever you're able to kind of give it a frame, it's able to do the inference, right? So in this case, if you see here, it's just as simple as that. Once it's handling talking to what's actually under the hood TensorFlow.js and WebGL, which is kind of below that, and handling grabbing the weights of the model as long as the model's public. And even here, we are not feeding it a stream. We actually are, if you're using a web browser, you can access the webcam with the like get user media call. And then we actually can say, give me a frame, give me a frame, give me a frame, right? And we're controlling the rate of that uh, by intentionally not grabbing them that often because we want to reduce the overhead and the amount of the cost on the CPU and GPU because this is the use case here was like, hey, it's kind of meant to be like sitting off in the background, right? So if you're using WebRTC, you actually still should have the ability to say, hey, I'd like sort of a frame, because even though you can kind of pipe it directly to the canvas, I may be misspeaking here, so I'm speaking from memory from the last time I did WebRTC, but then you would simply use Inference.js to similar to that, pass each frame. Because under the, computer vision models do still, for the most part, um, infer on frames. The same way like a large language model like infers on like sort of text input. And yes, you can do a whole bunch of trickery to keep expanding your context window. Most computer vision models are like you give me a frame and then I do a thing and I come out. So even the video is sort of chopped up frames. And the specialty with computer vision is these models that can actually do that inference 30 times a second and not once every several seconds. If I was directly sort of had effective, it sounds like a lower powered device running, it's like really running Python and wanting to run sort of computer vision on that, I would actually recommend in that case that you don't use Inference.js, which is you don't then need the overhead of being able to boot up the entire like underhood, even if it's headless, the Chromium runtime. I would actually recommend directly using the Python inference SDK that we have. This is actually optimized, just to run more directly for that runtime. But the goal I think for our company is there's a lot of work under the hood to make like all this inference tooling work well across all these. And normally you're right, like you kind of have to like figure all this stuff out by yourself. It's like, oh, I've done the work to train a model, annotated all of that, and like I have to figure out the import, export of weights and et cetera. So we have two public projects. One is our inference SDK, and the other one is called Supervision. That is a lot of the utility tooling to be able to run models. So in this case, define the part of the code, but you would simply just be able to reference, like, actually, it's right here. Here's the model ID, if it's a public model ID, and then here's sort of the image, which you can pass in various ways, and it'll handle like conversions over to the right underlying, effectively what is like a giant array of arrays, and it'll do the inference on it for you and kind of make all that nice and easy. Yeah, so I would definitely, if you're in a direct Python runtime, I would just use the inference SDK directly there on top of which is just a pip package you can install.
Nice. Yeah, that sort of overlaps with a question that I had prepared for you, which is like, I've seen situations where an enterprise wants to create a custom computer vision application to help verify that certain processes are happening correctly. Like
Mhm.
they have different components, and those components need to be put together in a specific order. It's like component A, B, C, A, B, C. And then if somebody's like A, C, it's like, oh, wait, hold on, wait, you forgot B, right? Um,
Mhm.
for these kinds of, I'd say like industrial kind of manufacturing processes, if somebody wanted to create, or maybe if you wanted to create an application to help with something like that, um, kind of like what would you do differently in terms of designing and, or maybe more importantly, deploying an app like this? This also kind of like ties into one of the questions I saw
Yeah.
about kind of like how to deal with like a new problem. Where do you start? What are some like the questions you start asking yourself or you start asking the user?
Yeah. So the way I think of this is, if the computer vision solution has to both grab its inputs and affect and outputs in sort of the same space or domain. So you think of like the factors there, like latency, what other systems does it have to touch when it actually detects something? Um, it's making the noise.
Time to drink. Drink some water.
I know. Yeah, well, all right. Versus other use cases. So you have like one element of like, hey, I have a computer vision problem. If it's in the case you just mentioned, it's basically like the thing has to, once you've trained the model, has to detect something in real time at a specific location, do the computer vision business logic and sort of AI processing, and then tell someone something on the floor in real time, right? And depending on even the speed of that, you have the factors of latency, what other systems it has to interact with, and what kind of like compute you have available. The the lower the latency, the more you need to interact with the thing that's right there in front of you. Um, and the more you have access to kind of compute at the edge, you kind of find yourself like going to like almost like the camera backwards, right? Where like your hardest problems will be how do I deploy this? And like put a fancy GPU at the edge with the camera there and et cetera, versus you might have other use cases where maybe you're a web app and you're like getting user generated media and you want to analyze it for a thing, or maybe you get a bunch of video and you can batch process it after the fact in your own cloud. Um, in that case, you kind of have the other thing where you were like, well, I don't want to do all that. Like the media is already collected. The impact in the real world is sort of like asynchronous from the collection of the media. Um, in that use case, you're more likely to kind of go to, hey, maybe I don't want to build all this out, and using right now, our cloud inference solutions actually makes a lot of sense, which is like, hey, I can collect, use the API to upload data, annotate. There's even automated annotation. I get a model, and I can literally get like an endpoint from you guys um, to just like hit and pay for credits or whatever, right? You can still do it yourself, but that's actually a really good use case. We offer deployment solutions on the other side. That's getting kind of salesy, but work at this company. So uh, the reason being that you kind of need a thing all in one that is handling the collection, inference, and impact into the real world. So you have to get close to the edge. In that case, you have to think about what cameras you're buying. You have to probably buy some Jetson devices, and you need a thing to manage the fleet of those devices and those models. So a lot of the tooling that we work on the enterprise is actually like focused around packaging the deployment mechanism in a way alongside building the computer vision sort of modeling solution. And it turns out you kind of need both for that use case. So I always have this like mantra, which is like if you need whatever your computer vision solution, like whatever the outcome is, the camera and the compute have to be there, like alongside that. Uh, so if you need to inspect something on the floor and tell someone, hey, you did it wrong, the camera and the compute have to be by the person on the floor. Um, if it's asynchronous, it's in the cloud, and you're telling someone in a web app, and maybe it's a mobile app or something, and you're going to do some computer vision and then respond, then you can put the compute in the cloud, right? I actually find like think of the constraints and the things of the camera of the input to your flow, and what things have to be impacted on the output of your flow. Otherwise, it's really easy to be like, oh, I've got a model. And then you're like, okay, like I can't make use of this. Like it made for a really cool demo, but it didn't actually matter. And that's kind of why some of the compromises that were very intentionally made here was to make it work in the browser, right? Because you kind of work from how someone would have to use it back to what are the constraints I'd have and what I have to build. Does that help at all? As like that's sort of the way I think of it when we talk to customers. It's very much like uh, going backward from the end impact, and what you can, and where the like, where's the input and output go, and then you
Mm.
can determine what the right metal is.
Yeah, no, I really like the way you phrased the sort of like you need your compute where your problem is happening, some stuff like that, or kind of like depending on latency. I think I've seen a lot of situations where we try to say something like, if latency is really important, like if that kind of like A, B, C process is going to result in immediate action needing to be taken,
Yeah.
there's a danger to somebody if they put it together in the wrong order. Um, I don't want to say like anything too gruesome, like they might get injured, they might get hurt, or maybe like if you put it together in the wrong order, the person will get hurt, but like maybe the machinery will get hurt, something like that. In those situations where latency is really important, then we're gonna want like the compute happening locally on that manufacturing line. And then if it's like you can kind of deal with some latency and you have internet access, then sometimes the cloud is going to make sense. That's cool.
That
Um,
tends to be it. Yep. Yep.
yeah, let me check out some of the questions that we got. People have been very intrigued about this project. I think we've talked about a few things that were related to deployment. Um, I kind of wanted to swing back around to like the model development.
Yeah.
I see there's one nice comment from Dalton. He just shared that he said he wrote a YOLO-based application to detect how much time my wife stays. He said my wife stays in front of the computer and alert her to get up, stretch, and rest for a certain amount of time. So that was very nice of Dalton to make that application for his wife. Um, so we had a couple things that were related to, let me see here. Um, I'm gonna try to like quickly summarize some of these things. All right, there was one from our good friend Zach, and he said my cup wasn't detected right away, but later it was. It made me wonder, would there be a way to update the model locally to recognize a custom cup a user has, or an entirely different approach to allow for this, trying to keep the spirit of not sending data externally and kind of keeping things in the browser. So hoping to not retrain the base model. I'm not totally sure about that. I mean, my first question is, I mean, my kind of first idea is we should probably just collect some data and retrain the base model. I'm kind of like not totally sure about like updating it on the fly.
It's a good question. So I would have, if I was faced with that problem, saying I just need more accuracy for me, right?
Mm.
There's sort of two solutions, and so one is, in terms of that one latency, there actually is that's one part that's intentional because in order to increase the likelihood that we really did detect a cup, we actually wait some number of frames after detecting it before we show it in the UI. So
Mm.
that's actually kind of an intentional where you're trading that latency for reliability. Um, and the second part is, I think I agree with you, Patrick. And this is one of those kind of interesting things, really, with like all models in general, is with computer vision models, like the training of the model kind of is a pretty intensive process that has to occur in some sort of cloud. Um, and so, companies like Roboflow try to make that super easy. You could build an application, by the way, which is like, uh, you violate one of the principles. It doesn't stay local, which is like, hey, we've trained it up to this level, making it easy to grab additional media from the webcam, and upload it to our tooling, and then let you kind of create your own data set where that you can that annotate in your own fork of the project, and then train the model, and then just say like, hey, great, like you can reference the model ID. Like there's just maybe here in the UI, you can overload instead of these being under the hood, you can add your own custom one, right? Um, but what that is fundamentally just saying, building a scaffolding on top of the process that was already done here to say, add more, fork this whole project, add more images, and train a model yourself. Um, that is pushing that all to the Roboflow cloud. I don't think you would likely within the world of um, most inference tooling have the compute necessary to do it locally. Because so I think that's unlikely. If you're familiar at all with like the world of like large language models that are not computer vision models, right? Like everyone's kind of thinking of ChatGPT or any of the other models. They face the same problem, and it's actually kind of fundamental, which is like they have context windows that can expand, and there is sort of learning that can occur within context window. Um, but then the base model, like if you want to fine tune that, it's actually more than likely you're going to break it. But what's on the other side is computer vision models tend to be the opposite, where they're sort of like, here's the base model, and they're designed for you to actually like fine tune them further. But they don't really have like true context windows, like a bunch of text. Uh, so some of that I think is the limitation of kind of all the current architectures that are sort of popular. I don't think you could fine tune it at the edge right now, but I could be proven wrong. Maybe there's something I don't know. There's things are changing all the time. So
Well, I like that you also just mentioned the idea of, like we said, maybe violates this kind of theoretical rule that we were just talking in of like we
yeah,
want everything happening locally, but I do think it's a rule worth breaking where we split up some tasks in terms of like training a vision model is really resource intensive. We should do that in a cloud service. We can collect more images and then add that to our training data set, retrain, and then release another model. Let's do one more kind of question before we wrap things up. I think maybe Jimmy had a couple questions again about model training, and I'm gonna read both of them here. How to train with another data set for false positives, annotation like this is not a cup. I have no cup in my hand. And then the other one was if I already have a trained model on cups, kind of like how to train for a new object and then keep the previously trained capabilities. For example, I can already do cups, but I also want some toys instead of, oh, and I want toys, but I don't want to lose like the cup capability. So could you kind of
yeah.
talk a little bit about kind of like false positives? Do you have any experience handling that?
That's something we didn't do and actually would be a valid enhancement, which is
Hmm.
we have some images in here that are actually intentional nulls, which is like images that we say, hey, there's nothing in here. And it's actually even a reasonable thing. In fact, one of the things we often recommend is like
Mm.
you could even have a class in your annotation called not cup, which is someone else is holding, other kinds of objects that are not cups, like hold I have a feeling that right now it'll fail on this because it would think it's a cup, it's just a webcam. Um, and that's actually a very valid tactic that in for most object detection models to actually train to intentionally add a class that is the thing that you don't want it to include and let it detect that class. And essentially when you're doing inference at the end, you say, well, I care about this, but it gives it sort of like a model, a way to classify something that it knows you don't want to have. So it's something we didn't do. The way you would do it here if you wanted to adapt this was you could literally fork this data set, add those images in, or find existing images maybe we didn't annotate correctly and intentionally add like you could be as dumb as calling it not cup. But it does work better for most of these models if you do annotate maybe a few things that you know are more likely to be false positives. And similarly, if you wanted to have toy, right? Like kids' toy or something like that, you would similarly fork the data set, add in those images and annotate toy. So just the fact that like it may be pushing out confidence and detections for toys at the end that you don't care about in the final output with certain levels of confidence, it's not a bad thing. It's actually making it easier for it to correctly identify cup. And I even hear simplified for cup, even though the cups can be glasses or other kinds of drinkware. Um, for some of the model types, I think for RF-DETR, because it adds, I think, a semantic distinction between them, I'd have to ask the engineers, like, we might have even gotten higher accuracy by detecting like cup, glass, tumbler as independent classes, because it could even get more accurate at detecting that kind of drinking apparatus, because they will all look more similar than just a general like type of drinking apparatus. So those actually are, I
Mhm.
think, like really reasonable enhancements um, that occur in sort of the data set. And like the true reality is like, well, this is like your data is kind of king with computer vision. Like if, there's like all these algorithmic enhancements, but like there's just so much low hanging fruit. And in this case, if I was to continue working on this project for higher accuracy, those are actually the kinds of things I would do is like keep tuning the data set to make it more accurate, include more images, and make it easier for the model to find the things I want by giving it more specificity in the classes that it could detect. So those are really good questions. Yeah.
Nice. Yeah, I had I think I was working on a project one time where I definitely had that experience of like, I think I was like counting like the knots in like a piece of wood, right? And it's like
Yeah.
I'm going for the knots. And then every now and then there's like another thing that looks kind of like a knot, but it's not a knot. And
Yeah.
it's like, well, here, like, I guess like the strategy was like, well, annotate my knots and then add a separate class for like it's the not.
Not. Yeah. I mean, if you can be more descriptive, like it's better to use a realistic word for these things.
Yeah, like dirt. It's like, no, that's not a knot. That's dirt over there, or like that's a
Yeah.
smudge, right? And then
Yeah.
it's like,
Yeah.
yeah,
Yeah.
yeah. Nice.
Um, yeah, because like the starting points for these things, especially the RF-DETR models, they do try to incorporate like the classes are not just like a unique token or something like that. They actually are trying to interpret that from the meaning of the thing to try to get a head start on that kind of object. So like the training data probably doesn't have a not cup in there, but it may have different kinds of things that, a smudge example might be a thing that is sort of, and that is trickier, but it'll be more accurate the more realistic your class names are.
Cool. All right. Well, I'm looking forward to seeing Jimmy's fork of this project that has some knot
Yeah.
cups in it. Everybody's welcome to do that. All right. Well, let's wrap things up for today. Riaz, thank you very much for spending your morning here with us talking about Hydrovisor and how you built this application to help remind people to stay hydrated. And congratulations on finishing that up and coming and presenting it. And it looks really cool and really fun. And then also thanks to our guests today who submitted a lot of really cool, fun questions and stopping by. So with that said, please enjoy the rest of your Thursday and remember to drink some water and to find some vision applications to go play around with. All right, take it easy.